All right, everybody, welcome to this afternoon session at AltConf. Our first speaker is Shepard, who I believe is here to welcome you to your first day at First Cat Savings Bank.
Close, yeah. Cool. Hello, and welcome. Congratulations on your first day at First Local Cat Savings Bank. We're so excited that you're going to be joining us here in our new office in San Jose to bring the next generation of savings accounts to our customers. So you might be wondering why we've hired all of you Swift developers. Well, we really love Swift. Our CEO got a little excited because he saw the bird and he kind of, yeah, he's a cat. So we really love Swift. We want it to be everywhere and used by everyone, which is why we've hired all of you to join us. And our whole banking platform is basically built on Swift. So this is a brief 30-minute induction session to go through step-by-step what you'll be building here at First Local Cat Savings Bank. And we'll wrap up today's session by looking at the company's culture and the future that we envision for Swift. So let's start at looking at what we currently build here. So you might be familiar with our original product. A user puts their deposit on the platter, the cat comes up, takes the coin in, and the money is deposited into their savings account. So customers have really loved this product, but we've gotten feedback from them and they want a bit more. They want something smarter. Ultimately, this original solution doesn't let customers know how many coins there are, what they've deposited, how much money, and they can't access this kind of information remotely. So we went away and we designed, we prototyped, and we came up with a new solution to solve these friction points for our customers. And we're calling it the SmartDepositPlatform. So let's take a look at how it works. So we have our original savings account product at the top, and it sits on top of the new SmartDepositPlatform. And just like always, the user puts their deposit into the savings account. That cat comes up, takes the coin, the deposit in. Yep. And then it figures out what the balance in the deposit is. That then gets uploaded and can be viewed on a mobile device. So what's under the hood of our new platform? So there's the hardware portion, which is the SmartDepositPlatform. There's the cloud, and of course, an iOS app. Now, the SmartDepositPlatform, as the user makes a deposit to their savings account, the SmartDepositPlatform calculates the value of their deposit. Once the value is calculated, it then uploads the information to the server. And then, of course, we have the cloud side, which maintains the customer's account, like deposit information, account overviews, all that kind of stuff, and gets it ready to be consumed by the iOS app. So I mentioned earlier that our whole banking platform is based on Swift, and this is because the actual physical hardware is a Raspberry Pi and running Swift. The cloud is Kitura using Swift, and the iOS app, of course, also uses Swift. So now that we've kind of seen what we're going to be building, of course, obligatory cat gifts, let's look at step-by-step how we can build this. So the first thing we're going to want to do is actually set up our development environment, because I imagine most of you are used to using Xcode on a Mac. Slightly different developing on a Raspberry Pi. So the first thing we're going to want to do is actually install Swift. So we can run, the first line is basically a script that goes and gets things, and then we run sudo apt install, and then the version of Swift. So there's a really great Swift for ARM community that's basically always getting versions of Swift ready for Linux. And so there's many different versions, depending on if you need 5 or a slightly older version. And it's pretty up to date now. It used to be a little slower to kind of get things ready and working on Linux, but it's pretty quick now. So once we have Swift installed, we can run Swift package init -- type executable. And so this will generate a bunch of different files and folders for us, like main.swift and package.swift. How many of you use the Swift Package Manager already? Yeah. There is support. I haven't actually tried it. There is support for like CocoaPods and stuff on Linux. I wouldn't guarantee how well it works myself, but the Swift Package Manager is kind of the reliable way that I found to always use for dependencies. Cool. So the Raspberry Pi. So this is specifically a Raspberry Pi 3B+. And on the left photo, I've highlighted the pins. So these are the GPIO pins, which stands for General Purpose Input-Output. And these help us communicate with sensors and actuators, like different electronic components. But it can start getting kind of tricky working with the pins directly because it's very small. So especially when you're starting out or if you want to prototype things, you can kind of use like a breakout kind of board with a breadboard, and you can plug things in. It's a little easier at the beginning to work with it that way, especially if you're kind of building more complex circuits. Cool. So there's 40 different pins, so there's quite a few different options. Some of them provide power. Some of them are just kind of standard GPIO pins. And then there's a few different kind of special ones, which we're not going to go into detail in this. Cool. Now, to be able to actually work with the GPIO pins on the Raspberry Pi, we're going to use something called Swifty GPIO. So to use this, we can add it to our packages.swift file, into our dependencies, and this will allow us to actually communicate through the pins. Now, Swifty GPIO is very cool. It's not limited to just working with the Raspberry Pi. There's a bunch of different boards that it works with, but basically any ARMv7, 8 running Ubuntu, kind of Debian, Raspbian kind of stuff. So yeah, so don't take that as the only ones it works with. Yeah, so it's a really great project and very, very useful for using the GPIO pins. Okay, so we've got everything ready, set up. Now we can start digging into how we're going to make the hardware actually work for the Smart Deposit Platform. So the first thing we're going to look at is showing the deposit status. So we're going to be using the 16:2 LCD screen. So on the left is the actual LCD screen, and on the right describes how we're supposed to wire it up, basically like which pins go to which pins on the Raspberry Pi. And then from the same wonderful person who made Swifty GPIO, there's also a helper library for working with the LCD screen, which simplifies it a lot. So we can wire it up. Doesn't look quite as neat as the nice little diagram before. And there are ways of making it look a lot nicer, but just for the purpose of getting things going, this works. So the code for actually getting this to work, we're going to import Swifty GPIO and the LCD library. We're going to initialize Swifty GPIO, set the pins up, and then we use the LCD. We assign the pins that it needs, and then of course we can just say lcd.printstring and provide it the text. Doesn't look too different from just working with kind of normal software. Okay, so our next step is we want to know what coin a customer is depositing. So there could be lots of different ways of achieving this. You could maybe use a camera and try to use some like cool kind of computer vision stuff to determine the coin. We're going to go a little simpler. So we're going to, each coin basically has a unique weight. So we're going to weigh the coins as they're deposited. And then basically the difference in weight will give us the value of the coin. So yeah, so we're going to calculate the coin weight by taking the weight of the entire thing, the savings account with the deposit. We're going to call that the current weight, and then we're going to subtract what the previous weight was before they had put the coin on. So for example, we've got maybe currently it weighs 1,003.5 grams, and then previously it weighed 994 grams. So I use grams because I live in the UK. Apologies if you're used to pounds and ounces. And so the difference between these two would be 9.5 grams, and that's what a 1 pound coin weighs. Cool. So how do we actually weigh something? Well, for this, we're going to use something called a load cell. So on the left is the actual load cell, the little silver bar with the wires. On the right is our CEO doing some beta testing with the load cell. So that's basically, well, in a very prototyping way, that's like a cutting board from IKEA that I cut in half and screwed the load cell into. But it's solid enough, so it works. So load cell works, basically inside there's a bunch of wires. So when you put a weight down on it, the load cell bends ever so slightly. So this is exaggerated quite a bit, but just so you can kind of see what's going on. So inside is a bunch of different wires, and as the weight goes on, the wires bend. And this bend causes a change in resistance, like the actual signal going through the wires. The resistance increases or decreases. And then that's what calculates the actual weight of the object. So the load cell is fed into an HX711, and this is an analog to digital converter that's specifically designed to work with load cells. So there isn't a magical library for the HX711. So this is a point where you kind of need to figure out, like, how does this thing work? How can I talk to it? And most of this can be found, really all of it can be found in the data sheet. So if you find a component that doesn't have a nice way of working with it, you can Google the data sheet. And data sheets are like instruction manuals for components. It explains like what it does, how to work with it. So you get like features, specifications, block diagrams, pin descriptions, assembly code. And in this case, this one also gives us a reference driver written in C. And this explains how we actually get values, like meaningful values, out of the HX711. So in essence, what this is doing is something called bit banging, which I'll go through step by step what's going on here. But it's basically where we're using software to directly set and sample the state of pins in order to get a usable signal. So with the pins on the Raspberry Pi, it only actually provides us with a digital signal. So basically it's 1 or 0. And this is different from like an analog signal where you could have any sort of value, like 768 or 140. So how do we get a value from basically 1s and 0s? So we can represent these numbers in binary format, right? So then we have a number that's just in 1s and 0s. But we need to go, I forgot how slow this animation is. So we need to go a little further because obviously if it's just a long series of 1s and 0s, it still doesn't help us because we're just sending them kind of one at a time. So this is where we need to have an agreed word length. So you say, there's this many bits in the word. So just in this example, this is a 12-bit word. So once we have that agreement between kind of the hardware and the software, we know when we have the whole number and when we can use it. So if we go back to our reference driver in C, and I do apologize for showing you C code, it's almost gone, don't worry. We can see the for loop is 24 times, so that means that we have a word length of 24 bits. Cool. So when we go inside the for loop, this is where the bit banging part comes in. We're pulsing the clock. We're telling the clock to go on. We read a bit in, and then we're pulsing the clock off. So yes, so we basically get each bit in, and then it gets shifted along one by one. I should have picked a shorter number. And then once we have all the bits in the word, almost, Okay, yes. Then once we have all of them, we run into this line, which is slightly confusing looking, possibly. But if we go back to the data sheet, it mentions that the output of these 24 bits of data is actually supplied in two's complement format. Now, two's complement is a way of being able to provide signed numbers in binary, because by default, they're not really signed. So this next line is basically how to get back from two's complement into, well, a signed value. Cool. So our, no more C code. Back to Swift. So the first thing we want to do is set up the pins. So we've got the data, which is in. So we want the data to come into the Raspberry Pi, and the clock we're sending out from the software. Then the actual code. So this is just kind of a quick prototype of what the kind of the C and what it would look like in Swift. So yeah, nothing too over the top ridiculous. And I'm sure there's probably nicer ways of doing some of this. But that will get you at least a basic value. So once we have our value, we can then consult like some sort of structure for the kind of coin weights and what they represent for values. So again, a very simple kind of way of doing it. And yeah, apologies, it's all in my money, not American money. Yes, and then of course we have our deposit entry, which conforms to codable. So this is a struct where we have like an ID, the value of the actual coin of the money, how much the whole savings account weighs, so that we can then use that to calculate the next one, and then like a date timestamp. Cool. So it's beautiful, isn't it? Very clean. This like brings a whole new level to spaghetti code. So we've hooked up our load cell, and we've hooked up our LCD screen. We've used GPIO to use Swift to work with all the different components. We've had a look at how to work with digital signal and do some bit banging. That looks a little tidier. Cool. So the next part is to look at how we make this data available anywhere. So this is not a whole talk about Kitura, because really to go into Kitura and how it works would be an entire talk on its own. But I wanted to give you kind of a few highlights about how we're using it to, like basically the power of using Swift across all the different platforms. So KituraKit is the client-side framework for sending the HTTP requests to a Kitura server. And Kitura and KituraKit send and receive these instances of Swift types directly. So the types can be shared between the client and server, and it's beautiful. And it's so much less code. I don't know how many of you have like spent loads and loads of time integrating APIs, third-party APIs, even like internal ones, and just the amount of code and like JSON and all of that kind of stuff. No, it all goes away. It's beautiful. So this is just kind of a very quick example of what we do on the Pi. So when we're sending the deposit to the server, and then when we want to get the deposits back from the server on the Pi and iOS. So it is there's more code than this, obviously. But this is just like, you can just work with like types, and it's not this huge, messy thing. Yes, so now we've had a brief look at how we got the server kind of stuff working. I wanted to take a little bit of time to talk through kind of the longer term, why we use Swift and what we see as the future for Swift. So we want Swift to be everywhere and used by everyone. And ultimately we think that this will make the language better, right? More people using it should make the language better. And that we'll have a more diverse community as a result. Because really, like, if we just have like a very small subset of people teaching computers how and what to think and making these things, it's very dangerous, right? The world is full of lots of different people from different backgrounds who've experienced lots of different situations. This is just a really brief example that I saw the other week. So this is, somebody did research into basically what happens if you verbally sexually harass a voice assistant and their responses to it. And it's pretty shocking because you can tell that most of the teams that worked on these things clearly haven't experienced verbal sexual harassment, because you wouldn't, I mean, they're meant as jokes, but it really normalizes that that it's saying it's okay to basically say these things to somebody, and especially since most of these voice assistants, like by default, are women, it's also not super great. Yes, so it's a great example of why it's important to have more diversity in your team, because you don't produce things like this. And ultimately, at First Local Cat Savings Bank, we don't want to enable this kind of technology. We want to create a better future. We don't want people to feel alienated. So Swift is still relatively new. It's 5 years old now. Was it 5? 2014? Yeah. And it's changed a lot over the past few years, thanks to an amazing amount of involvement from the community. But the barrier to entry is like quite high if you really want to get into developing Swift. So I want you to spend just a couple moments thinking about like what do you want Swift to look like in 5 years from now? Like, don't just think about the language, but think about the community. Like, who do you want sitting next to you here? Where will Swift be used? Will it just be iOS, Mac developers? Watch and TV too. I like the TV. So I kind of see two futures in a very, one or the other. One where it's really just, and no offense to us, we're all very cool, but we're, a subset of people. So I see one where it's just us still working with Swift, but there's another possibility where it's everywhere and it's used everywhere, and it's more popular than Java, because Java is currently ranked as the most popular language. So this kind of only us currently using Swift in the future, it doesn't look like we're creating a language or a platform for people other than ourselves. And to me, this is like very scary, and I worry about the future. And I'd mentioned that the barrier to entry is quite high. Like the cheapest Mac is that's really, really small on my screen, is $799. That's really expensive for somebody, for most people. And like schools, Macs aren't in schools. Like if people really want to get into programming, it's not accessible. So how do we get to this kind of Swift being everywhere, people being able to learn it anywhere? Well, the Raspberry Pi starts at $5. That's a pretty low barrier to entry. That's still challenging for some people, but it's a huge step forward in just financially the accessibility of being able to develop for Swift. But the tooling on Linux leaves much to be desired. So a lot of the people who are writing Swift for like Raspberry Pi and Linux are using Xcode, and then just kind of pulling the repo on Linux and running it from there, which works. It's what we're used to, but it's not helping enable this kind of next generation, this kind of other group of people to be able to come to love Swift the way that we love Swift. So there's a lot that we can do to still grow Swift that isn't always just submitting proposals to Swift Evolution. Ask yourself, what can you do to help build the community? What tools can you create or contribute to, specifically on Linux? Is there somebody that you can teach? like ultimately, what can you do to help Swift evolve? So that is my talk. I do have some stickers, if you want a cat sticker. But yeah, I encourage you to really think about the future that you see for Swift and really how we can get there. Yeah, thank you.
We have time for some questions, if there are any.
I'm also around the conference, so if you have questions, you can just come and bug me.
All right, so there are stickers on the table, and let's thank Sally again.
Thank you.